Okay, so Ron and I will be presenting on how we applied microsimulation to analyze multimodal operations associated with an event center and a baseball stadium that's currently under development. The project is located in Oakland, California, and it's the future home to the Oakland Athletics MLB team. The presentation will cover our overall approach and some modeling techniques that we use to analyze an environment with vehicular congestion, heavy pedestrian flows, and TNC activity. So to kick us off, Ron will tell us a bit more about the project.
The project is located in an industrial area where there is only one travel lane per direction with limited pedestrian facilities. The project is proposing to construct over 1 million square feet of office use, 2,500 housing units, ground floor retail, hotels, and other amenities such as parks. Next slide. As the table presented for the game day traffic, the project is truly multimodal, where we have drive, rail, TNC, walk, bike, ferry, bus modes. One of the things that we suggested is to cap the parking spaces to 7,600 to limit the amount of vehicles coming in and out of the area. But the goal was to mainly model the 35,000 fans start departing the stadium, getting into their transportation mode, and eventually leaving the study area. Next slide.
So the key elements that we wanted to capture in the modeling process were the transit operations, TNCs, particularly during a pre-game and a post-game scenario. We wanted to develop recommendations for the roadway and pedestrian infrastructure and help refine the design alternatives. Our analysis also fed into a transportation management plan. And lastly, we developed some visualizations to communicate the results of our analysis. The Visa model had about 40 intersections. The stadium is located here. There are some rail crossings, a couple of pairs of freeway ramps. So there's quite a bit going on here. Since pedestrian operations were of interest, we included details such as the measurements of sidewalks and crosswalks and the waiting areas. We also included obstacles such as trees and other objects on the walkways to more accurately reflect the available pedestrian space. We also modeled the TNC pickup and drop-off areas and a TNC staging lot. The VSIM analysis was a 5-hour study period from 3 p.m. to 8 p.m.
The VSIM model calibration, while complex, it was similar to most other projects. We needed to adjust the vehicle fleet to reflect local conditions, driving behaviors, car spacing, and some safety lane changing maneuvers. As well, as we all know, this is an interactive process that helps us achieve model validation. The interesting part was the pedestrian calibration, as this is new for us. We collected data at congested pedestrian areas such as other baseball stadiums and major transit stations. We replicated some of the crosswalks and sidewalks and calculated level of service from observations. Then we used BizWalk with the default pedestrian behavior and small tweaks to it. Overall, the default pedestrian behavior performed acceptable and replicated the level of service calculations we got from observations. Next slide.
So there were some big implications of TNC activity on the auto and pedestrian operations. So we had the challenge of realistically modeling TNCs. There's a TNC staging area that's planned a few blocks from the stadium where TNCs would receive ride requests from passengers who would then get matched to a designated pickup spot based on a first in, first out system. To implement the ride matching algorithm, we took advantage of a couple of features of the software, one being the ability to create user-defined attributes for various elements in the VSIM network to update the attributes during the simulation using either the inbuilt formulas or the Python API that we use to interact with the simulation. I've got a quick video here to show our initial concept for how we implemented the TNCs. In this video, the TNC lot is located near the top right of my screen where the TNC vehicles will be arriving from. The blue areas represent pedestrian waiting areas, and the tiny dots on your screen are the pedestrians leaving the stadium. And as we were building our simulation, we added some labels to flag which areas have a ride request and a pedestrian waiting. We also have some labels to show which of them have a TNC vehicle assigned to them. And lastly, some labels to show the occupancy of the TNC vehicle. So these visual elements helped us troubleshoot our code during development and also to monitor the results. And these are some of the measures of effectiveness that we use to evaluate the different scenarios. For vehicles, we looked at demand served, delays, queues, speeds, and travel times. For pedestrians, we looked at demand served, particularly in the post-event scenario when tons of pedestrians are leaving the stadium, and also pedestrian density, which is a measure of the space available for pedestrians and how freely they're able to maneuver.
The scenario development was interesting as it was a merge of the project trip demand plus needed mitigations. We started with existing conditions, then added the project trips. We considered that the project did not achieve acceptable results whenever we obtained a gridlocks. The picture on the right bottom corner, it's a common cross-section of the industrial area. No sidewalks on one side and very narrow ones in the other, causing major complications for the thousands of pedestrian demand. It was relatively simple to identify mitigations at the early stages. Whenever the network ended up on a gridlock, we proposed mitigations that help resolve them. And as you can imagine, we will fix a gridlock 1,000 feet from the project site, and the next one will appear 4,000 feet from the project site on the next model run. Vehicular mitigations were challenging in the sense that there was no space for road widening. So we were limited to a few turn pockets and signal coordination. Some adjacent small streets had to be closed to limit the amount of vehicle conflicts and alleviate the vehicle flow. For safety purposes, many closed space signals had to be implemented to help organize pedestrians and vehicular modes. Otherwise, pedestrians will not let vehicles cross the street. Most of the signal will be operational only during the major events. Next slide. The figure at the bottom middle of the page is a typical outcome of the model pedestrian run, where they went to the corner and they can no longer move through the conflict pedestrian flow and created a gridlock. Then eventually pedestrians start queuing up on the sidewalks and we can see the deteriorating of the density. The goal of the project, again, was to safely and efficiently move pedestrians and vehicles in and out of the project site. And later we're gonna show how we achieved that. Next slide. Pedestrians normally take about 3 hours to get in and out of baseball events according to the data that we capture for the A's during the 2017-18 season at their current location. Therefore, game-related vehicular activity takes about the same time. This causes some overlap with the local traffic peak hour at 5 p.m. One of the goals that were imposed to us was to have the system recover between 6 and 7 p.m. as it currently occurs during existing conditions. Then and only then, we were achieving a recommended plus project scenario. I would like to share the final plots that help visualize most of the MOEs that we presented on the report. Let's start with pedestrian density plots. On this figure, we have on the top right corner the pedestrian density scheme, where level of service A is a dark green to level of service F, which is red. The figure shows that we were able to achieve level of service C or better from the hours of 3 to 4. Next slide. From 4 to 5 p.m., we were able to achieve level of service C or better at all the sidewalks, yet some of the corners start experiencing level of service D. There aren't an established threshold for pedestrian density, but what we notice is a level of service E or worse resulted from pedestrians waiting over one traffic signal cycle at the corners. The next hour is the last hour for pedestrian activity, and here we can see that the system has fully recovered, the pedestrian demand has decreased and has been served, so we were able to efficiently satisfy the pedestrian demand without major complications. Now let's move to the vehicular activity. In a similar fashion, here we have vehicle speeds where vehicles traveling really slow, speeds from 0 to 5 miles per hour are read into like free flow conditions that we consider 20 miles per hour due to the industrial area where posted speeds oscillate between 25 to 30 miles per hour. The figure from 3 to 4 basically shows normal activity where we have some slowdown, some congestions at the signals, but nothing major going on. We see some red activity at the TNC areas due to the high demand and vehicles stopping. The next hour, 4 to 5, it starts getting interesting because at the freeway on-ramps, either the 980 or the IA80 southbound, we see some congestion starting to form. The TNC areas are still congested, but for me, the interesting part is that the exit of the ballpark is getting red. Why? Well, the rail tracks adjacent to the stadium, they serve passenger and freight trains. At 4:15, we have a 5-minute freight train that holds traffic, shades the exit of the baseball, and creates long congestion. Unfortunately, after the train departs, we cannot just provide green light for 5 minutes to evacuate the traffic. Otherwise, we will collapse the local system. So with signal coordination and keeping pedestrian-friendly cycles of 90 seconds through the network, we try to flash as much as possible. Now let's go to the peak hour, 5 p.m. Here we see that the bottlenecks from the freeway ramps have grown decently and they are about to merge into each other. This was the most vehicles we can flush without half the two freeway on-ramps jump into each other and create gridlocks through the downtown. There are some trade-offs here that we have to do into sacrificing delay for baseball fans leaving the stadiums and keeping operations stable for local traffic. The next slide. Here is a 6 to 7 p.m. where we see the bottlenecks have decreased. We're almost achieving existing conditions. Currently, existing conditions, the freeway ramps disappear, the congestion disappears by 6:15, 6:20. Now with the stadium on place, it will disappear 6:40 to 6:45. So not extremely horrible, and we were able to evacuate all the all the vehicular activity from the stadium. The last hour is 7 to 8, and this one was basically a request to make sure that this plot matches existing conditions such that there is the confirmation no demand from the stadium is affecting any traffic past 7 p.m.
Real quickly, the results of the pedestrian density analysis were used to inform the design and sizing of treatments such as sidewalks, landscaping, crosswalks, and curb extensions. For vehicles, these included signal retiming, restriping, bus-only lanes, bus priority lanes, and on game days, we recommended treatments such as variable message signs, traffic control officers, and turn restrictions. Lastly, we wanted to touch on some takeaways from this work. This was a good proof of concept for modeling a congested multimodal environment with thousands of pedestrians and TNCs. Ron, did you want to say something about the calibration?
Oh yeah, the model was 5 hours long and it would actually take about 8 hours to run one version. So sometimes the amount of pedestrians and vehicles was so high that it will run lower than real time. So when we get the average of 10 runs for robust results. It took a couple of days, so schedule implications are certainly something to consider for future projects like this.
And so, but that said, like the scenario management feature definitely helped us, efficiently code and maintain and modify several scenarios. The programming interface was another one where we were able to use very simple Python scripts and formulas to modify to model the desired TNC right matching algorithm. The algorithm that we used was a pretty simple one, but we think that the same concept can be extended to some of the more advanced and open-ended TNC right matching algorithms. Yeah, that pretty much concludes our presentation. Apologize for being over time.
That's totally fine. Thanks, Sai and Ron. And just for everyone, we do have a little bit of extra time available on the last two presentations of the day. So we're going to spend a couple extra minutes on this one. If for no other reason, I'm going to call moderator rights and say Oakland A's are my favorite team. And you guys, hopefully you guys did a good job, because even though I don't live there anymore, I'm going to be down visiting and make sure I can get in and out. But my question is, always had big concerns, they're moving the site from something that was BART adjacent over to a very constrained, industrial waterfront area, freeway on one side, and they're adding all this office, it sounded like from your project description. Can you just talk for a minute about why you picked the time frame you did? Because it almost sounds like you figured out the maximum situation was going to be at the end of a day game on a weekday, and I'm not sure. Like, to me, that without thinking it through, that seems a little off. Like, I would think it'd be more a weeknight game or something of that nature. So maybe you can just from that perspective. Give me some.
I can take that question. So basically, we actually modeled both the scenarios, a midday game and a night game. And what we found out is that evacuating the stadium, it's a lot harder than getting people in. Normally, for the game days that start, evening games that start at 7, people will heavily arrive after 6, so there will not be much overlap with the peak hours. So we try to, the project is extremely large, and we just try to present the hardest of the two situations. But yeah, sure. There was definitely the other scenario study as well.
Okay, great. Look like that was my question. Look like somebody else from our attendees added something very similar. It says, look like you concentrated on weekday day games for your study. Do the recommendations change for weekday night or weekend day or night games? So you talked a little bit about weekday night, but what about weekend stuff?
One of the reasons why there was so many signals closely spaced is that in order to evacuate this many people from, like you said, not an ideal land use, the specific signal plans for every scenario were important. That's kind of like the main management. Now, in terms of pedestrians, the curb extensions, sidewalk widening, and all the other suggestions we provided with the help of BizWalk, it applies for both in and or out pedestrians. So it seems like everything was able to be managed.
Okay.
Yeah, I think ultimately this ended up being the most congested and the most critical scenario because of the overlap with the vehicular or the local peak hour and the other vehicle traffic.